Hello everyone and welcome to Introduction to CFD. This is going to be our second lecture, and this is going to be the first time that you're going to actually have hands-on experience in the software that we're going to use throughout our course. Okay, so like I said before in our previous lesson, as of right now we're going to be doing a series of problems each lecture. That's going to show you the capabilities of CFD. Okay, we're going to start from very simple problems, but that already have an engineering standpoint, and we're going to increase the difficulty of our lectures, okay, of our problems. So we're going to start very simple, and then we're going to make each harder. We're going to make harder each lesson, okay? So the first problem that we're going to tackle is the problem of the static mixer. Basically, what we have here is a tank that's going to receive water or any type of fluid, as a matter of fact, that is going to have two different characteristics. They can be different fluids. For example, we could be mixing water and air, for example. Or they can be the same fluid but at different temperatures, for example, which is the case that we're going to study right here. We have this static mixer and we have two inlet pipes. They have the same flow rate, they have the same velocity, which is 2 meters per second. However, they have different temperatures. So in one pipe we have water entering at 2 meters per second at 315 Kelvin, and then we have on the other hand the same flow speed, but the water is at 285 Kelvin. And we have the outlet pipe down here. Our tank has a radius of 2 meters, and what we're going to do is we're going to determine the speed and temperature of the water that exits the flow mixer. Okay, so let's get started. First, we're going to open the software, okay? There are two ways that we're going to be working here. Either we're going to be working the software in its workbench form or in its standalone form. For this first tutorial, we're going to be using the standalone form, okay? So what you're going to do is you just type the Windows key, type CFX, and choose CFX 2020 R2, okay? There you go. So now you have this window right here. So the first thing that you're going to do is prepare your working directory. So how do you do that? Well, first you're going to look at the files that I sent you, which is going to be this one, static mixer static underline mixer underline standalone r170.zip. You're going to extract it, and what you're going to want to do is you want to copy the folder, the address folder where you put your files, and then you're going to go back into CFX and going to put it right here. Okay, there you go. So you're going to have your working directory be the directory that has all of your files that you're going to use in this tutorial. Okay? Oh, very well. Now we're going to define our CFX Pre Setup. Okay? So how do you do this? You click right here. You have these four options. You have Turbo Grid, CFX Pre, CFX Solver Manager, and CFD Post. You're going to select the second one, CFX Pre, right here. It's going to open. Enjoy the sweet sounds. Very well. Now that you have it open, you're going to create a new case. How do you do this? You can either click right here, new case, or you can come here and select File, New Case, or even you can just type Ctrl N. Okay? since this is the very first problem that we're working with, we're going to be doing it in a very, very simple way. So we're going, instead of using the general option, we're going to use the quick setup option. So you come here, select quick setup and click OK. You can click OK here as well. It's just warning you that default domain is active. Okay? Don't worry about this right now. So we have the first screen of our first tutorial, okay? So right now we're going to choose if our problem is a single phase, multi-component, or a multi-phase problem. Since we're going to be working with only water, with only one phase, then we're going to use the single phase problem type, okay? The second thing is that we're going to choose our fluid, our working fluid. Like I said, we're going to be using water. So we're going to change from air, ideal gas, to water. If you don't see water from the 3, you can come here, click on the ellipsis. Then you're going to have all the materials available. You can expand water data and you can select water right here, okay? Very well. Like I said in our first lecture, we're not going to create our own meshes. We're going to use pre-existing ones. So what you're going to do here is you're going to click in the folder, and since our working directory already has all the files that we need, we're not going to even need to look for it. It's going to be right here in front of us, which is the static mixer mesh.gtm. If you don't see this file when you click on this folder, is because your working directory doesn't have the mesh file. So what you can do is you can search for it right here, or you can go back here and change your working directory to the one that has your mesh file, okay? So coming back here, we're going to select static mixer and we're going to click it open, and there you go. This is our static mixer, okay? You can use your mouse. If you left click and hold the left click, you can drag around your domain so you can see it better, okay? So you can see our 2 inlet pipes and our outlet pipe down here. You can also use the predefined cameras down in the bottom right corner. You can ask him to put the Y axis pointing to you, or the Z, or the X, or you can put ISO, and even you can click on with the right button anywhere around here, go to predefined camera, and you can choose from here. For example, isometric view with the X axis up, or with the Z axis up. For example, the Z axis one, I find it to be the best one to see the whole domain in a non-confusing manner, okay? So after your mesh loads and you play around with to get familiarized with it, you can click next, okay? You can also zoom in with the roller of your mouse, or you can even choose these ones right here. So if you want to see one of the inlet pipes, for example, and you can return it to its normal state by clicking this magnifying glass with the cube in it, okay? Very well. Now we're going to define our model data, okay? We are going to specify the flow as a steady state with turbulence and heat transfer. The turbulence model that we're going to use is the K epsilon turbulence model, and the heat transfer is going to be the thermal energy model, okay? The K epsilon turbulence model is a very common used model and is suitable for a wide range of applications. The thermal energy model neglects high-speed energy effects and is therefore suitable for low-speed flow applications, which is our case right here, okay? So make sure that you have your analysis type as steady state, okay? And obviously make sure that you have your physics definition panel showing. So you're going to make sure that your analysis type is steady state. Your reference pressure is 1. So all other pressure settings are relative to this reference pressure right here, okay? The heat transfer, we're going to select thermal energy, and the turbulence model is already the one that we're going to use, which is the K epsilon model, okay? So just click next. Right now, we're going to define our boundary conditions, okay? So what we're going to do here is we're going to delete both of these pre-existing boundary conditions. So you just right click on it, select delete boundary for inlet and for outlet, okay? So then you right click anywhere in this white screen and you select add boundary, okay? Name it in1. There you go. Why did we choose in1? Because the pre-existing mesh already has pre-existing names. So if I choose in1, you can see that the location is already selected for me. You can see this green highlighted face right here. Let me show you what would happen if I chose a different name. For example, let's say that I put this my name, Xavier. If we go here, it doesn't automatically select the location because it doesn't have a Xavier named face. So what we would need to do is we would have to click on the ellipsis, and then we're going to need to look for the face that we are interested in, which would be in 1. But if you already choose the right name, we can bypass this step and we can move along faster, okay? So create a new boundary, name it in1, and make sure that the location right here is in1, which is this highlighted face right here, okay? If you want to see the same way that I'm seeing, remember, just click the right button here, Predefined Camera, Isometric View, Z up, okay? Very well. Now we're going to change the normal speed. Remember that in the beginning of our lecture, I showed you that the speed that the water is entering both of the pipes, it's 2 meters per second. So we come here and we change it to 2. Also make sure that the unit is correct. So make sure that the unit is meters per second, okay? Very well. Now we're going to set the temperature. The temperature is going to be 315. However, you can see here that is in Celsius, okay? We're going to set it in Kelvin. So what we need to do is type 315 and then choose K, which is Kelvin, okay? Very well. Now we're going to create the other boundary conditions, the second inlet and the outlet. The process is the same. So you click with the right button anywhere in this right window. Just make sure that you're not selecting the in1 boundary condition, because then you will only be able to delete it. So you can click, for example, in the boundary, and then you can right click, add boundary. Then you're going to type in2. And you're going to see that, wait a minute, Professor Xavier, the location didn't choose the in2. If I go here, I see in2 right here, but why didn't the location automatically select it for me? Because I used the uppercase letter. And you can see that it's case sensitive, right? So make sure that you know the case that your boundary, that your face is described. So go to add boundary, and now I type with the correct case, and there you go. Now it's selected for me. Okay, make sure that you're changing the conditions for in2. You can see that the normal speed is already correct, but like I said, the water is coming from the pipes at two different temperatures. The temperature for this one is 285, okay? And now let's create our third and final boundary condition, which is the outlet one. The name you're going to choose is out, A-U-T. And you're going to make sure that you change the boundary type. It's no longer an inlet, no longer fluid is coming in through this pipe. It's actually coming out. So we're going to change it from inlet to outlet, okay? And then you're going to leave average static pressure to 0 Pascal, okay? So click next. And then we're going to enter the general mode by clicking finish. You can see now that we are at this is the traditional UI that we're going to use throughout our system. All the stuff that we did before was the quick setup boundaries, okay? This is going to be the one that we're going to use the most because it's the one that we have the most control of, okay? The quick setup is fine for introducing the software, but gives you very little control on your problem, okay? As you can see right here, we have these black arrows that are now showing up in our domain. And they are a good guide to you to make sure that you selected the correct boundaries, that you select inlet where inlet is supposed to be, and that you selected outlet where outlet is supposed to be. How do you check that? You can see that the arrows are pointing towards the domain in our two inlet pipes. This means that these faces right here are inlet boundary condition faces because they're pointing towards our domain. The outlet condition boundary, however, points outwards. So this is a good check to see if you selected the boundaries accordingly, okay? Well, since we already used the quick setup guide to set up these conditions, we don't need to mess around with these options right here, okay? What we're going to change is we're going to set our solver control, okay? The solver control parameters, the solver control parameters control aspects of the numerical solution generation process, okay? We're going to use an upwind scheme, which is less accurate than other advection schemes, but is also more robust. So this advection scheme is suitable for obtaining an initial set of results, but in general, they should not be used to obtain the final accurate result. So they're a good starting point, but they are not the option that you're going to want to use at your final product, okay? We're also going to set the time scale, which can be calculated automatically by the solver, or we can set it manually, okay? The automatic option tends to be conservative, leading to a reliable but often slow convergence. It is often possible to accelerate this convergence by applying a timescale factor or by choosing one manually. That is more aggressive than the automatic option. But in this tutorial, we're going to select a physical timescale leading to convergence that is going to be twice as fast than if we used the automatic option, okay? So for this problem, we're going to set our timescale. We're not going to use the automatic option. So how do we do this? You can click 2 times with your left mouse in solver control right here, or you can go right here in solver control and right click it. Okay, so on Advection Scheme, we're going to change it from high resolution to upwind. Okay, like we said before, it's more robust, it's faster, but less accurate. Okay, then we're going to find convergence control right here, and we're going to change our time scale control. Okay, we change it from auto time scale to physical time scale, and we select 2 seconds. Make sure that you have the unit correct right here, seconds. You have seconds, minutes, and hours. Select seconds. Okay, and then you can click apply and OK. So basically, this is all we're going to need to do for our boundary setup. Okay, now we're going to write the CFX solver input file, which is the point DEF file. Okay, first we're going to save our case right here. Actually, this is something that we should have done before. Like when we open the CFX software all the way back in the quick setup, it's already a good thing to save your file. So we're going to save our file right here. I'm going to name it static mixer underline lecture 1. Okay, and we're going to save it. Okay, after setting up the solver control, what we're going to need to do is define our run, which is basically telling our computer, okay, our setup is ready, now you can run our simulation. So how you do this is you go right here in define run. Let me see if it shows up. There you go, define run. You click it, and then you're going to save it as the same name from our CFX Pre file. Okay, so we set static mixture underline lecture 1.def, and then you save it. Okay, now it opens up the CFX solver tab. Right now we're going we're not going to mess around with this one. But because our problem is very simple, so we don't need to ask our computer to run it with more processors, for example. We're just going to run it like this. Okay, so we're going to click here, start run, and then you're going to see the window how you can check your simulation while it's running. Ours has already finished because in our CFX solver we actually didn't select, but from its default configuration it says the following. Okay, when our residuals go below 10 to the minus 4, we can say that our simulation has converged. So we're going to stop if our simulation, if our residuals go down if our residuals go below 10 to minus 4. So you can see that the RMS W momentum crossed the threshold between 20 and 25 interactions. The same goes for the RMS P mass, but the RMS U momentum and the RMS V momentum only cross the threshold after 30 interactions. So that's why it will only be, our simulation will only be done after all of these residuals cross our 10 to the minus 4 threshold. However, the best practices tell us that it's better to choose 10 to the minus 6. Okay, is a more accurate convergence criteria than 10 to the minus 4. But this is just a tutorial, and 10 to the minus 4 will be good enough, okay? And this is the first screen that I want you guys to show me, to send me via email, okay? So what you're going to want to do is very simple right here. You're just going to print this screen. You're going to type, you're going to press the print screen button on your keyboard, and you're going to save this file and you're going to send it to me, so I know that you have ran the simulation as well, okay? Very well. After this, we can close the CFX solver and open the CFD post. How you do this is you can just click this icon right here, launch CFD post with a results file. And then you click OK. Now we're going to visualize our results. This you can see that is a little bit different from the previous image, because right now we are interested in the fluids that go inside our domain. We're not interested in the domain walls, for example. So this is why from a default standpoint, you can only see the borders of our tank and the borders of our inlet and outlet pipes, okay? But we're going to change this a little bit. We want to see a little bit more. How we do this? You can right click on Wireframe, edit, and you can change this edge angle from 30 to 10, and then you can see that it at least is showing us the walls of our pipes, okay? And this is better for us to visualize the problem in itself, okay? You can change these numbers to 45, for example, or you can change it to, let's say, 3, and then you get a much more detailed view of the domain. However, this is going to obstruct some of the stuff that we're going to see, that we want to see when we analyze the problem. So let's leave, let's say 15%, 15 edge angle. There you go. This is going to be good enough. So right now we're going to create a point to represent the origin of a streamline inside of our domain, okay? So how you do this? You go insert, and then you select, and then you go to location, and then you select point, okay? The name doesn't matter, you can leave point 1. Make sure that the method is X, Y, and Z. So we're going to select the coordinates at X, the coordinate at Y, and the coordinate at Z. And the coordinate is going to be -1, -1, and 1. -1, -1, and 1. Okay? Pay attention that we don't have anything inside of the domain, but when I click apply, there you go. We have created a point inside our domain that is very near the outlet of the left inlet pipe. Okay? Very well. Now let's create the streamline itself. Again, you go to insert, and then you select streamline. You can leave the name the same, and then you choose start from the point that we have just created. So I didn't change the name of the point, so it's point 1, and we select that one, okay? We're going to change what we see from velocity to, we're going to change here in color. We're going to change user plot variable to variable, okay? And then you're going to change the variable from velocity to total temperature, which is right here, okay? It's different from temperature. You want to choose total temperature, okay? Then you're going to want to change the range. You're going to, if you choose global, it's going to look at the minimum value on the entire domain. It's going to look at the maximum value of the entire domain, and it's going to make it and it's going to adjust the streamline according to these two variables, just to show you the difference and how you can get better results, more information, just by changing this range. Okay, so let's leave the range at global. You can see that our streamline is basically yellow in the beginning and then it's basically green, okay? But if we change it to local, see, we get a much more wide range of information. We can clearly see where the streamline is hotter and where the streamline is colder, and this is not very clear if our range is in global. So make sure that your range is set to local, okay? And you can see that is working as intended, with the higher values of temperature closer to the higher value of temperature of our inlet pipe. Here we have 315 Celsius and here we have 285 Celsius, if I'm not, sorry, Kelvin, if I remember correctly, okay? You can also change the position of this point. So if you go back here in point, right click it and select edit, we can change this position. Let's say we're going to use -1, -2.9 and 1. Okay, and we're going to click apply. See, we pushed our point further into our inlet pipe, and you can see that inside our inlet pipe the temperature is almost constant and is almost equal to 315 Kelvin, because all the water inside this pipe is at this temperature. When it leaves this pipe, it starts to get in touch with the water, with the colder water from our other inlet pipe. So it starts to get colder as well. Okay. Now we're going to put it back in our original position, which is -1, -1, -1, and we're going to click apply, and you can see that it goes back to the position that we previously established, okay? We can also change the appearance of this legend right here. So how do you do this? You go here to double click default legend view, okay? Change the title mod to user specified, and then we define this name right here. So let's put it streamline temperature. Okay. Select horizontal, and in location Y justification, put bottom, and then you can click apply. You can see that we have changed the position and the appearance of our legend, and this is very useful, especially when you want to generate images and information for your paper or a report that you need to hand to a client. Okay. Now we're going to create a plane that is going to slide through our domain. So in CFD post, you can often view results by calling a graphic object. The graphic object could be an isosurface, a vector plot, or in this case, we're going to use a plane. So the object can be of fixed color, or we can vary its color based on the value of a variable, okay? We already have some objects defined by default that you can see listed in the outline, and you can view the results of the boundaries of the static mixture by coloring each boundary object by a variable, okay? To view results within the geometry, you will create new objects. So you can, for example, let's hide both our streamline and our point, and let's make it show us the inlet face, okay? Better yet, let's make it show us the outlet face. So if you double click here and change the mode from constant to variable, we can see the distribution of pressure, for example, in our outlet pipe, or the distribution of temperature. Again, if we choose the global range, we get very little information, but if we choose local, there you go, we have a much wider range of information right here, okay? With the highest temperature closer to the warmer inlet pipe and the colder temperature closer to the colder inlet pipe. So we can see that this information is actually making a lot of sense. But this is not what we want to see. We want to see what is happening inside of our static mixer, okay? So how are we going to do this? We are going to create a plane ourselves. To do this, we can go insert, location, plane, or we can just click here, location, and plane, okay? If you want, you can change the name. Let's change the name to slice, okay? Now we're going to use we're going to define our point right here, okay? So we're going to use the XY plane method and leave it at 0 for now, okay? So you can see that it's placed at the bottom of our tank right here, right before the outlet pipe funnel starts, okay? But let's change this position. So instead of choosing the XY plane method, choose the 3 points. I'm sorry, not 3 points, point and normal method, okay? Under point, the coordinates are going to be 0, 0, 1. And the normal is also going to be 0, 0, 1. There you go. So we have our slice plane that is passing through right the middle of both our inlet pipes. Okay? Very well. Now we're going to configure this pipe. How do we do this? We're going to change our colors, our color scheme, okay? Actually, before we do that, I want to show you that you can render this slice plane, okay? So go here in the render tab, and then you go right here, not here, you can go to show faces. You clear show faces, and then you go to show mesh lines, and then you change the color mode to user specified, okay? Click on the ellipses, and you can select any color that you want. Let's select, for example, green, and you can type OK, and then click apply. There you go. Now you can see the mesh in the slice plane. And why this is important? Let's say that you're creating a mesh for your domain and you don't know exactly where you need, and you know the regions that you want it to be refined, but you don't know if the software is actually refining them in the places that you want. So what you can do is you can create, for example, a plane like this, ask the software to show you the mesh in this plane, and you can see the mesh throughout this whole slice. So you can see, okay, the mesh inside the pipe is good enough for what I want from my problem, okay? And you can zoom in to better see if the mesh is accurate. For example, let's change the color back to black. There you go. I suggest you change it to a different color because black is already the streamline, the wireframe of our domain. Okay, let's go back here and let's change this back to show faces. Okay, so this is what we have. Now let's change the color of this plane from constant and a constant gray to the temperature, not total temperature, okay? And click apply. There you go. You can see very clearly where the cold water is coming and the hot water is coming and how they mix inside our static mixer. Okay? You can also change it to local, but in this case it's not going to change very much because the local region already encompasses the lowest temperature value and the highest temperature value. So the local is equal to the global in this plane, in this position of the plane. Okay, so leave it at global. You can also do something to get more detail out of this plane. So what you can do is adding a contour instead of using a plane. A contour connects all points of equal value for a scalar variable, for example in this case temperature, and help to visualize variable values and gradients. Okay, so color bands fill the spaces between each contour line, and each band is colored by the average color of its two bounding contour lines. Okay, so let's create a contour. So we can go right here and click contour, or we can go insert contour. Okay, I'm going to change the name to slice. Oh, we already have used the slice, so let's change to slice contour. There you go. So now we have the contour tab open right here. So what we're going to do, we want to change the location to the plane that we just created, which is slice. We're going to change the variable from pressure to temperature, and we're going to click apply. And you're going to see that is a little bit convoluted because the slice is still showing. So you clear the slice and you can already see that you have much more information. So just as a comparison, this was the slice and this is the contour. You can see, for example, let's take a look at the blue areas. You can see 1, 2, 3 different blue areas, different cold regions, while in the slice you basically only saw 1, maybe 2 if you count these 2 right here. Okay, so let's go back to contour, and you can even improve the level of detail right here. How you do this? You increase the number of contours. Okay, oh, excuse me, I accidentally hid the legend, which I did not want to. So let's say if we went from 11 to 100, pay attention to what's going to happen inside of contour, but also what's going to happen with our legend. See? Now we have 100 divisions in our legend, and we have 100 divisions of contour colors right here, so we get a much more detailed view of our contour plot. Okay? Let's go back to, for example, 10. You can see clearly like all the contours right here. You can see like 1, 2, 3, 4, 5, 6, 7, 8, 9, and I probably missed one. That would be the 10th one. Okay? But let's leave it at 100. There you go. It's a much more detailed view and much more richer in terms of information. Okay? But let's do one more thing here. CFD is a very special tool because it provides you with a lot of ways to show the information that you have for your problem. So what we're going to do is we're going to create a very fast, very quick animation to show this plane moving from the top of the tank to the bottom of the tank. Okay? So let's go here in Tools and select Animation. Okay? So what you want to do is you're going to first need to set up the camera that you want. For example, do you want to show the information like this? Do you want to show the information like this? Do you want to show the information like this? So on and so forth. We're going to keep using the one that we had chosen before. Okay? There you go. So right now, what we want to do is we're going to create the first keyframe. Okay? Keyframes are required in order to produce the animation. You need to define the first viewer state and the second and final viewer state, and set the number of interpolated intermediate frames. Okay? So we already have defined the camera view. Now here in the outline, under you want to expand this one. Okay? Yes, right here. You first you want to click on keyframe animation. Okay? And now you want to create a new keyframe. Okay? This is going to be our first keyframe. Okay? But like I said before, we want to show this plane going from the top of the domain to the bottom. And as of right now, it is not on the top of the domain. So what we're going to do here is we're going to go back to our slice, and we're going to change the point coordinate to be 0, 0, and minus 1.99. There you go. So our slice went all the way to the bottom of our domain. Okay? Now, actually, let's do this differently, because this way we're going to show it going from bottom to the top. And what we actually want is to go from the top to the bottom. Okay? So instead of minus 1.99, you're going to use 1.99. There you go. So it's all the way up at the top of our domain. Okay? Now make sure that you selected keyframe number 1 and click right here, set keyframe. So what you just did was that this image right here is the image of the first keyframe. Okay? Now what we're going to do is we're going to create our second keyframe and final keyframe. For that, you go new and go back to your slice, change it to minus 1.99, click apply, make sure that you have the keyframe number 2 selected, and click set keyframe. Okay, now what you have here is 2 keyframes. Okay, the second keyframe is this one, and the first keyframe is the one with the slice all the way at the top. Okay, so let's see how this animation is going. Let's click play right here. See, way too fast, right? So how do we change this? You select keyframe number 1, and then you change, let's say, to 20 frames and click apply. I'm much more slower. You can see way better. Okay, so let's put it, for example, let's select keyframe number 1 again, and let's put 50 frames. Let's play. There you go. Way more slower and with a lot of information. Something that you might be asking yourself, Professor, why don't we use the local range right here to get more information inside all of the planes? It is a very reasonable idea. However, if you change it to local, let's see what happens. Actually, we need to change this one to local as well. There you go. And we're going to want to change the slice. We're going to want to hide the slice, okay? I'm going to press play again. See? Doesn't change much because... I'm sorry, this is set up wrong. Yeah, now we're good. There you go. So let's go back to the first keyframe. Let's press play. See? No. Bear with me 1 second. Like, we need to change this to local, apply, and then we need to change this to local, apply, and then we need to set the keyframe. This is what we were doing it wrong. We need to set the keyframe. We weren't setting the keyframe, so it was always going back to the one that we originally created. So go to the second keyframe, local, apply, set keyframe. There you go. Now, let's press play. You can see there's a much more information, correct? But because our legend is also changing, we will not be able to compare, for example, this red value right here to the red value that happens at the top of the domain, because they are different, okay? So for this type of information, it's better to set a maximum value and a minimum value and not have them change, so that you can compare the differences in temperature in different positions of our slice, of our plane, okay? So let's go back and set it to global, apply, set keyframe. Let's select the first one, global, apply, set keyframe, and make sure that is correct. Okay, there you go. What you can also do is you can save your animation, okay? Actually, let me up you one more. Let's mess around with our range. So let's go here and let's create a user specifying range, okay? So like I said before, we are going to choose the minimum value and the maximum value of our scale, okay? So for the minimum value, let's choose 295, and for the maximum value, let's choose 305, okay? Now we click apply and we click set here. Let's do the same for the first keyframe. Minimum value 295, maximum value 395. So there you go. The second keyframe, we didn't add that much information, but we add plenty of information to the first keyframe, which I forgot to set up again. It's set. Okay, there you go. There you go. Now we're good. So now we have fixed both the minimum and maximum values of our scale, okay? And now let's go back here and run our animation. See? Up until the entry of the outlet pipe, we have a lot of information, and as you can see right here, our scale does not change. So we can actually compare the values of each plane to another one. Okay? Now we can also save this movie. How we do this? We check this option, save movie, right here, and then we're going to save it. I'm going to save it at our working directory. Okay? You can see that is working. There are working directories already selected, which again goes back to show you the importance of selecting a proper working directory. Okay? So we click save, and you can choose how many times this animation is going to loop. For example, if you leave 1, it is going to go from top to the bottom and is going to stop. But to me, this is going to be very fast. So let's say that I'm doing a presentation and I want this to keep going a little bit while I convey an idea. So let's change this, for example, to 5. Okay? And there you go. Click here for it to go back to the beginning, and then click apply. You notice that the animation is slower because at each iteration, at each frame of animation, we are saving our file, we are saving our movie. So it goes from the top and then goes down 1 frame, and then actually he goes to he's at the top, the animation saves, then he goes down 1 frame, the animation saves, it goes down another frame, the animation saves, and so on and so forth. So that's why when you select to save the movie, it's going to take more time for the animation to conclude. So that's why before you decide to save the movie, you make sure that the animation is working the way you want. Okay? And now we can check our animation. We can check our movie. You go here. This is our file, staticmixer.wmv. We can select our movie and we can play it. The quality is not very good because it's a tutorial and I didn't want it to take a lot of time, but we can actually make the quality of this animation way better. Okay, it's going to take more time for the file to be created, and the file is going to be heavier, but the results are going to be way better. Okay, and you can also see our legend right here, the fixed values of minimum and maximum temperature as well. Okay, so basically what I want from you in the CFD post is I want you to send me this movie via email, and I also want you to send me the slice images both at 1 right here. So I want you to send me this image. You can by doing a print screen again, I want you to send me an image of the plane all the way at the bottom, which is minus 1.99. So I want you to send me an image of this one. And I also want you to send me the image of the streamline with the point, okay? So I also want this image right here. So I want the point streamline image, I want the contour, oops, I uncheck the wireframe. I want the contour at the bottom. I want the contour at the midpoint of the inlet pipes. I want this image as well. And I also want the animation file, okay? You can send me this all via email, okay? So I will evaluate your progress, okay? So to resume, I want, I think, 5 files from you from the simulation, okay? I want this file, this screen right here, okay? I want you to send me the print screen of this image right here, okay? All of it, and the images that I just described here, plus the animation file, okay? So this is it for our second lecture. Thank you guys very much. If you have any doubts, you can send me an email, and best of luck.